It is my pleasure to introduce Marius Hugo this morning.
Marius is a product of Hermanus. He grew up here and he went to school here. And then he went to Stellenbosch, where he completed his industrial engineering degree. He spent 3 years in the United States of America in Boston in research and design, focusing on smart material applications. Then returned to South Africa to obtain an MBA from the University of Cape Town and set out working in private equity, the finance of energy projects, and clean tech funding. This was followed up working for the World Economic Forum in Geneva, Switzerland for a period of 3 years. But his interest was to get back to commercial applications of engineering, and some 7 years ago, he took on the challenge of commercializing ocean wave energy here in Hermanus. Back to his roots, and this is the topic of his talk today. Marius was recently appointed Chief Operating Officer of Abergold Limited in Hermanus, and in that position, he will continue to develop the harnessing of ocean wave energy. Marius, we look forward to your talk. Thanks. Over to you.
Thank you very much, Peter, and thank you very much for having me. This project has been a passion and a pleasure to work with, and I also like to welcome my father, Hugo. He's also on the call, who was the visionary behind the concept. And even though I started my tackling of the project in about 2013-14, he was doing environmental impact assessments and community participation for years before that to get all the permissions in place for the pilot project in Hermanus. Welcome, Pierre. So I'd like to focus today on a bit more broader than just the technology. Focus on the project in Hermanus, where we've come from, what we learned. I've got some videos to share with you, specifically on how the technology works. And then some of our more innovative construction techniques that we had to develop in order to move towards a commercially viable application. So let's jump into it. Let me just see if I can move my slide on. So yes, we're based here in Hermanus, and we've had about 6 years of research and development in this wave energy technology. The key thing I just like to focus on here is the technology itself is relatively simple, and I'll talk about that now. The challenge and the research that we've been doing is more about how to commercialize the technology. So as with any renewable energy project, or any project for that matter, every rand and cent that goes into the construction of the project needs to be repaid by the revenue generated from it. So in an energy project, if a project costs 30 million rand to build, you need to pay back that capital through the rand per kilowatt hour that you sell the power for. So if a 1 megawatt project costs 100 million rand to build, I would have to charge 20 rand a kilowatt hour. And as we all know from our monthly municipal bills, no one is going to buy power at that cost. So that is really the state of ocean wave energy globally right now. And the challenge, the race is to achieve a cost competitive rand per kilowatt hour from ocean wave energy technology. So that's the key, and you'll see a bit more detail as we continue. I'm not going to spend too much time on this side of it. I assume that the renewable energy imperative to get away from carbon dependence, to prevent or hopefully even reverse climate change, or the impact that we've had on the climate change. And then more interestingly, on the right-hand side of the slide, some of the renewable energy technologies like wind and solar definitely have some limitations. So, solar, the sun only shines for 8 hours, if we're lucky, per day. And that's already a 30% or 33% starting point. And then because of the angle of the sun, that reduces all the way down to 15% availability or capacity factor, which for running, let's say, an abalone farm, that creates a host of other problems because we're running a 24/7 pumping operation. Energy storage is of course one of the big solutions to those limitations, but it comes with a big cost, as well as some environmental impact in the manufacture of battery technologies, and there's a host of new innovations in that way. So that's really the problem as we've defined it, and the reason we believe wave energy might be part of the solution. So the first thing, and I referred to it in the previous slide, ocean wave energy, as you can see at the left there, has a much higher capacity factor compared to hydro, wind, and solar. When I actually built this slide, I was quite surprised to see hydropower having such a low capacity or an availability factor. But that has obviously got to do with seasonality, especially in South Africa. You can imagine the Orange River during the low rainfall months being a fraction of what it could be. So that's the result of the capacity factor there is a result of seasonality. Wind at about 34% and solar at about 25%, I'd say, is very generous. But that is obviously highly dependent on where you are in the world. The waves, they just keep coming. It is an incredibly consistent energy resource. We've mapped about 15 years worth of ocean wave data from a macro point about 17 kilometers out in the ocean. And it's a 3-hourly data available, and the fact is that we get very, very few days per year that we won't be able to generate power. So our capacity factor or availability factor here in Hermanus, I'd say, is much higher than the 60% on the slide, even though, yes, at some days you'll have more power available when the waves are bigger, and less when it's smaller. The other massive benefit that ocean wave energy has is its predictability. So wind and solar to an extent, even though, as we all know, especially here in Hermanus, the weatherman is often wrong. But when it comes to the long-range wave forecasts, we can, within about a 10% accuracy, predict almost 10 days ahead. Now, for industry, that's very important because you can plan. You can plan your backup power, you can plan your operations accordingly, and that makes it a very attractive resource itself. The last aspect is it's abundant. So wave energy, as you can see from the following slide, which is the global wave energy resource map, says, okay, well, where is wave energy viable? Wave energy is measured as a kilowatt per running meter of wave front. So if you're standing on the beach and you're looking out at the waves, every 1 meter of the wave in front of you has a certain energy capacity, and that's what you're seeing here on the map. The dark red being 60 kilowatt per meter and up, going all the way down to the blue being below 5. So ocean wave energy is viable anywhere where we're seeing red, orange, yellow, and dependent on the technology, even the green. So yeah, there's the application for wave energy in the open water or on the coastline is huge. Interestingly, 60% of the world's population lives along the coastline. That's just human nature, and thus a lot of the market that could benefit from wave energy doesn't require large transmission systems. In our case, Johannesburg might be one of the big exceptions. But there we are, as you can see on the map, how fortunate we are. It almost scarily how blessed South Africa is with solar and wind, and as you can see now, wave energy as well. I see it almost as a responsibility that South Africa has to learn how to harness this. And then once we are able to do so, I think the application thereof in the rest of the world is fantastic. So let's focus a little bit on our specific wave energy converter technology. So while I talk, I'm going to, in the background, play a video. If somebody on your side can just confirm for me that the video is playing correctly, I'd appreciate that. Is it visible on the screen?
It's playing, yes, it's okay.
Okay, so this is our site in Hermanus. We've had a digital overlay of what the plant might look like. And as you can see, it's essentially a dam or a reservoir on the shoreline. Okay, we've made use of the natural geography of a little bay in front of the harbor. And as you can see now, we're going to have a section cut of the functional wall that we see. So the waves run up a slope of the wall, then into a dam or a reservoir through a set of valves at the back. The wave can either run up and over, called overtopping, or in our design, it can go through the wall itself and then have a set of one-way valves at the back of the wall, which prevents the water running out the same way that it came. So if the dam is full, the valves are shut and the waves need to go to the next level. The water then runs through from the reservoir at the back of the dam through a very simple hydroelectric turbine. There's a couple of different design options here, but it's as simple as that the kinetic energy from the wave is captured into potential energy in the reservoir, converted to hydroelectric energy through the hydroelectric turbine. So one other aspect to the design is the little triangular dam that you see on the left-hand side of the screen. We call that a turbine stabilization dam, and that dam is there with one-way valves leading out to the ocean, so that the water can move back to the ocean. But when a wave approaches that wall, the valves close and prevent the water from going in. So essentially, the reservoir is got the highest head possible, with the waves filling it up, and this little dam on this side has the lowest possible. And right in between sit the hydroelectric turbines, which creates the head difference you need to generate power. Okay, I'm going to move back to our slides. And there we have it, just in word format. The kinetic energy of the wave is driven up the slope and captured into potential energy, almost like a pumped storage scheme that we have on the way to Cape Town at Palmit. and then the water is converted to hydroelectricity when it flows backwards back to the ocean. That concept is called overtopping. It's not something that we came up with. It's one of the 4 or 5 main types of wave energy in the ocean, but we've optimized it quite significantly with the multi-layer concept, with the storage of power in the reservoir behind, which helps with smoothing the output of your energy. So the bigger the dam is, the longer you can bridge the lull in the waves without affecting your energy output. So it's almost like a capacitance effect that the reservoir dam has on your electricity generation. I think before I go on to the more detailed side, I'd just like to pause and maybe it's worth playing the video in the background as reference. But when Pierre and all of us were envisioning this type of technology, one of the wave energy potential, if I said, one of the big decisions that we had to make was, do we go offshore? So most of the wave energy technologies are based on offshore equipment, something that bobs up and down or opens and shuts or moves with the open water wave energy that moves more in up and down direction. That was the one option, so open water, versus a kind of nearshore or onshore solution. The massive benefit that you have on the open water systems is that you don't have as much kinetic energy to deal with of waves actually breaking. So you also have a massive scaling factor in the open water systems, where you can really cover square kilometers full of devices in order to generate power. However, the big drawback of an open water system is cost and environmental. So from a cost perspective, you're dealing with underwater cabling, you're dealing with mooring, so big concrete blocks that hold the device in place with very, very strong cables. You're dealing with needing dry dock facilities, divers, boats, and maintenance costs that escalate quite dramatically. So if we add all that up without even considering the cost of the wave energy device, open water wave energy is a very, very costly exercise, and thus this current state of wave energy, or the current commercialization of wave energy, is facing those challenges. So we decided to stick to what we know and to sidestep a lot of those issues by building onshore or nearshore. Now, we sidestep a lot of the cost issues, but that does create significant challenges in constructing in a very energetic surf zone. And that's where our challenge currently lies. Luckily, there's enough coastline, as you have seen, to make use of. And eventually, the system itself becomes an ecological system, which would have very low visual and noise and environmental impact. To carry on with the slides. So our business model is currently at a point where, as I've said, we've completed about 6 years of research and development into the construction technique. If we have got some time at the end, I'll go into some of the history there. But as I said, it was a lot of trial and error as far as construction is concerned. We've patented a lot of the new construction techniques that we've had to develop, and we've prototyped some of that actually in situ in the sea, actually building up quite a lot of know-how in how to do this, which is one of the big benefits we've gained, other than actually knowing what to do. The know-how in working in that surf zone is what I believe one of the very valuable lessons that we've come out with. So the next step for us is to actually complete this 1 megawatt pilot project at a commercially viable cost. Now, the question I often get from especially people that are in the construction sector, is that people build harbor walls all the time. Why are we struggling to do so? Why are you struggling to build a wall in the ocean when people have been building walls in the sea since the Roman time, maybe even earlier? The simple answer really is cost. So and I'm going to just skip to one slide further so you can see an aerial view of our site. Our pilot WEC site is over here in the top left-hand corner. This next site here is the next project. So once we achieve the first one, we'll move on to this one. And this hydroelectric project was completed actually, a while ago and has been commissioned. The reason I want to show you this map for now is the challenge in using traditional techniques of construction, which essentially is either end tipping. So what they do is they take rocks and they put it in the ocean, throw and build up a rock bed, protect it with dolosa in front of the rocks, and then cast a concrete layer on top of those rocks. Now, if you're building building a solid wall, that definitely remains an option, where our wall has got a lot more functionality to it. But more importantly, the requirement for dolosa, which are essentially breakwaters to protect the wall, does the exact opposite of what we're trying to achieve. In other words, we're trying to harness that energy, that kinetic energy, and not disperse it before it gets to the wall. And then the only other option would be to essentially is put dolosa out in the ocean, build behind it, and then remove them. But then you're getting back to your cost challenge. So we did cost those, and definitely not a viable option from a commercial perspective. The other technique that we've often considered and wished was commercially viable would essentially be to fill the bay with rubble and rock all the way till past where you want to build, then excavate the line where you need to build the wall, build your wall, and then remove all that rubble and filling again afterwards. Once again, cost prohibitive to the nth degree. So we have sat with every civil marine engineer that would give us the time of day, and we've brainstormed this over and over in a variation of approaches, and what we believe we've come up with is the only commercially viable executable construction technique that we are ready now to actually try in the ocean. I'm going to get to that point. The slide is really just about the investments going into renewable energy. As we all know, it's going in one direction, and for a variety of reasons, from an environmental perspective, from a cost perspective, from a dependence on carbon perspective. As you can see, heating and cooling being probably the biggest opportunity in that. sorry, I'm skipping through a couple of slides here, but I'd like to focus a bit more on the technology side. Yes, we do have competitors. As you can see, a variety of projects happening all over the world. Wave being probably the most prolific, but tidal is also very interesting, especially if you've got a very high tidal variance. In South Africa, our tidal variance is only about 1.6 meters from between the high tide and low tide, which doesn't give you much to work with from a kind of a head perspective to generate hydroelectricity. In areas where that's viable, you have tidal variances of 8 to 16 meters. And that's where some of these mega projects in Europe are looking at tidal as a very viable option. So yeah, here's the slide I actually wanted to get to. What we've come up with from a construction technique is the fact that the most challenging construction aspect is the foundation of the wall. So we're building a wall on a very uneven rock surface. So the first thing we need to do is get a foundation layer in upon which we can start placing our wall blocks or units, as we call them. Now, we spent many years, and I'll get there if we've got time at the end, looking at casting our foundation underwater in situ within a box or a caisson, waiting for that to cure, and then placing your blocks on top of that. But because of the energetic surf zone, that technique proved to be incredibly difficult to get right repetitively. We did manage to get it right to a degree, but I realized that for all the stars to align, and working in front of an abalone farm where water quality was paramount, the risk in that construction technique was too high. We needed to be able to, with absolute certainty, when we go into the sea, in a very short time period where we have flat seas, be able to go in, place a foundation block, and build with enough weight on top of that to not be washed away when the waves pick up. So I'm going to show you a bit of an animation of our current technique. And then I'll show you how far we are in the realization thereof. So you'll recognize the dam building in the background. And now this is a crane that we have with a robotic arm that probes the seabed. So essentially it's taking depth shots in a grid pattern of the uneven rock bed. So instead of casting in situ, we're now taking a map of the seabed itself, recorded automatically by the robotic arm. That information is then directly used in a concrete mold, which the floor of the mold adjusts to that information that we've just got from the ocean. The concrete can then be poured into the mold, as you see on the screen. And now you've got a foundation block of about 40 to 50 tons that gets railed out back to the crane, picked up, and placed perfectly on the seabed, almost like a jigsaw puzzle. Then the crane brings precast blocks and packs it as a fashion. I wish it happened this fast, but that was really just to illustrate that technique. I'm going to replay it just to illustrate it once again. So you have a crane which essentially has an automated probe that follows a very strict grid pattern, probing the rock bed. The size of that probe foot is quite important. If it's too big, you don't have enough touch points. If it's too small, it will take too long. So we believe anywhere up to a 500 millimeters by 500 millimeters foot plate will give more than enough stability for that foundation base. That information is translated to your mold, which we will automate, so we won't have to manually make all these adjustments. You'll see there's actuators at the bottom of the mold which push the columns up, and then lifting it and putting it on a rail down to the same crane on the site is relatively simple, as long as you have a big enough, strong enough crane, which is also relatively available. I was initially quite, I thought twice about the idea of making 40-ton blocks, thinking it's absolutely massive. But most of the guys that work in the rigging industry will readily tell you that that's not a problem, and that they work with 100 tons or higher quite easily. So that is the concept that we came up with. We actually executed a similar technique that wasn't automated, where our probe was literally a staff going up and down, almost like a surveying staff that took the measurements. But we found that manual process, A, took too long, and B, wasn't accurate enough. So then we came up with the robotic technique. We imported a used robotic arm from a VW factory in Hamburg. I was quite blown away by how easily available and affordable they were, especially in their used or refurbished state. So people often look at it thinking it costs an arm and a leg, but that setup, as you see there, was only about 250,000 Rand to get here and to implement. So I'm going to show you one more video of how this is the last video of how this arm works. I just want to put the sound down, otherwise it's quite loud. But essentially this is, or maybe I'm not sure if you can hear the sound in the background. Can I maybe put it up? Can somebody confirm?
No, you didn't click the sound, so it doesn't come through.
Okay, now then I'll talk us through it. So as you can see, the robot is pre-programmed to work to probe in a grid fashion, which are those black lines on the floor. We dropped rocks in place to make sure we have a random pattern to profile. And then as the probe goes down, it senses when it has resistance, and then stops, records the depth, and then lifts up and moves into its next position. This is a very slow process. I'll actually later in the video speed it up quite significantly. You'll see now. So it starts moving at about an 80% speed, and that motion can actually get you the entire 4x16 meter grid pattern within half an hour to an hour. The data is automatically recorded in a sub-millimeter accuracy, which is phenomenal, and that data will be used directly to build a foundation that we refer to. Pierre helped us build a mock-up of that automated concrete mold, and those yellow and green columns move up and down automatically based on the depth profiling information. And then that bow tie looking structure on the top is one of the precast units that fits on top of it. So this gray area, I'm not sure if you can see, between the yellow columns and the green bow tie becomes the solid concrete block that fits perfectly on the rock profile below the water. So I had a lot of fun doing that. One question I often face is why automate? Now, having worked in the ocean and tried to with the human element for the last 5 years, it's a very dangerous environment for people to be working in the wave zone. We need to be incredibly accurate, and it's an incredibly repetitive process as far as getting these depth shots. So if anyone knows anything about robotics, the actual definition of robotic applications is exactly that. The robots are good for tasks that are repetitive, dangerous, and accurate. So the penny dropped, and we slowly started looking into it, and which led us to this concept of an automated profiling technique. Now, the key to why this is a commercially viable construction technique lies in the ability to get into the ocean when you've got a flat period, profile your seabed, cast your concrete block, wait for it to cure, and then move it and place it in the ocean in 1 8-hour stretch. So from the historic data, we've learned that we have about only 8 hours every 2 weeks of ocean conditions that are flat enough for us to actually work in the sea. So if we miss a single 8-hour period of working in the sea, or if, let's say we miss every second opportunity, would double our project time and thus our project cost. So being able to profile this the rock bed reliably and accurately was the first challenge. And we believe we've got a very, very reliable technique to do so. The next challenge was, how do we cast a concrete block and get it to cure into a usable strength within, let's say, 4 hours on the same day? Now, that's made possible by a concrete accelerator. It's the same type of concrete that they use to fix bridges and airstrips, where they've got a very, very short window period which to go in, do the concrete work and get out before it needs to be used again. The concrete is more expensive, probably about 4 times more expensive than your Portland cement or concrete mix. But since the volume is relatively small compared to the rest of the wall, because we're only using it for the foundation, that suddenly became a very viable option. So with a crane, an automated profiling robot, and fast curing concrete, we believe that we can, every 2 weeks, when we have our 8-hour window, get in, profile within an hour or two, cast the block, the foundation block within 4 hours, have that out, ready to be placed in the ocean, and then place your precast concrete blocks on top. So we'll actually progress with 2 meters every 2 weeks of the wall, which gets you about a year to complete your construction of the whole wall. And that the key to the commercialization of this technology. So it sounds like a lot of things need to stack up to do that. We'll start this process by doing the profiling, making sure that's right, potentially having the concrete block cast by someone else off-site, installing it 2 weeks later, if we need to in order to trial the technique. But that 8-hour process from profiling to packing is really the key to making this project commercially viable.
Can I quickly ask you, do you use
Yes.
reinforced concrete, and how do you place your rebar if it's reinforced?
So yes, we will reinforce it. The rebar is assembled within the top layer of the foundation block. So it's essentially almost like a concrete slab on of a house. So you have preformed rebar shapes that sits in the top of your foundation block. It's also possible that once you've had the floor of your mold adjusted, and there are very deep areas which needs additional reinforcement, to place a rebar shapes within those blocks before the concrete is cast. So you've got your kind of reinforcement cage, is what they refer to it as, in the top of the mold. And then if you need any addition, we'll add that before it goes straight in. So it's a very modular kind of concept. We've also actually done quite a lot of that previously. We've cast these foundation blocks before with relative success. It took us a lot longer than the potential of an automated profiling technique. And we'd all packed these molds by hand with little shims. It took us a very long time. So the idea of automating that whole process that we've already gone through is the key to what we need to do. So this is the project timeline. Just to give you a sense of actually the budget that we aim to complete it in. If you sum these 3 phases that we need to tackle, it comes to about 50 million rand. Of that 50 million rand, within this, you'll see there's a purchase of cranes and gantries, which are reusable equipment. So what we're trying to do is bring down the cost of a 1 megawatt project to about 35 million rand for a 1 megawatt project, which brings your rand per kilowatt hour to 1 rand or lower. So that's our goal. Our goal is to produce ocean wave energy at below 1 rand per kilowatt hour. And if we can do that, we have got a viable, scalable technology and construction technique, which we believe we can roll out anywhere in the world. As a company, we often get asked, are we going to be a project company who goes from site to site building these ocean wave energy converters? The project is, the answer is maybe much more mixed. The idea of we've patented the technology, we could lease the technology to others, we could look at the engineering services that come along with the project. We don't necessarily have to own the project ourselves. We could do project development for third parties. There's also a nice opportunity, I believe, for establishment of equipment fabrication, especially around the hydroelectric equipment, turbines and such, within an area just outside of Cape Town, where when you have your wave energy projects up and down the coast, you have a central manufacturing hub for the industry, as well as potentially even maintenance contracts to maintain these plants up and down the coast. So the business has a lot of potential in itself and for its investors. This presentation I'm actually showing you is what I've been using to approach investors over the last year or so. Unfortunately, COVID has slowed my progress significantly, till the world comes to its senses again. But I believe the fundamentals are still in place, and we're kind of almost at the precipice of achieving what we've been planning to achieve for the last 5 years. So we have a great team still involved. This is our board, and we have a fantastic situation with Abergold as the off-taker of our energy. Once we have our pilot project up and going, we've got the potential of selling electricity for the next project to the municipality or the other abalone farms. So we've got a fantastic environment in which to prove that this technology works very well. Our current funders to date have been the Industrial Development Corporation, management. We've had a fantastic support from mostly local angel investors or private individuals that have backed the concept, the team to realize this vision that I believe has got so much potential. The industrial partner here is actually it's Abergold. They're kind of the project was initially envisioned as part of Abergold when Pierre was still involved, and then we established Mean Sea Level as a separate entity to pursue wave energy independently. So Abergold, as the industrial partner and off-taker, is obviously still rooting for us to solve their energy problem. As I've discussed, we've got a 3-phased kind of project rollout that needs to commence as soon as possible. And that's really the end of it. I see we've got about 10 minutes left. I can maybe just, while I take some questions, I've got a few slides of pictures from the history of our attempts at construction techniques in the ocean. You'll see there as far back as November 2015, where we were casting concrete underwater in these big cages. Those are sheet piles that we put around the concrete, around the section that we were going to cast in. The waves, the day started off lovely, and as you can see in the bottom right-hand corner, the waves picked up and taught us a bit of a lesson in how to work quickly and efficiently in the ocean. I told you about our probe. This is our manual probe that you see here on the left. We placed this cage over the ocean and had a grid with which we probed the ocean seafloor to get that information to cast our foundation blocks. Here you can see in 2019, our construction technique was relatively successful, and we got about a 16-meter section of wall into the sea. You'll see there one of our concrete blocks lying against the side. You'll see the profile of the seabed as one of those foundation blocks that we cast and did. But eventually, this technique that we developed, its Achilles heel was the size of the blocks. They were about 8 to 10 ton blocks that we had to hold together with hydraulic post-tension. But maintaining that tension in the ocean, where you've got essentially an earthquake every 12 seconds, like a wave, just turned out not to be a sustainable solution. So one of the big improvements to this technique, which was, we felt we were almost there, was to replace this 20-ton excavator, which we used to put the blocks in, scale up our blocks to 40 to 50 tons, which we are very confident once you put a 40-ton solid block in the sea that interlinks with the others, you will have a solid construction with which to move forward. So that's it. Thank you very much. I think, Peter, with your permission, we can open the floor to questions. I hope you enjoyed that.
Thank you very much, Marius. I immediately have a question, and that is, how do you prevent leakage at the bottom? Do you actually grout it up afterwards? And also the contact between the blocks, do you actually grout that up so that the whole thing is connected and integrated?
Yes, so you only need to be waterproof right at the back of, if you can see at the bottom left-hand side of the wall. So once the wall is actually built, we'll go in afterwards and grout with relative protection from the sea. Now we can work safely behind the wall and go in there and grout in between the blocks. One of the big benefits of going much bigger and more accurate with our current improved design is that you do also have many fewer joins that you have to seal afterwards. But the design also is having your valves at the back of the wall, which also assists with that. So where your valve bank then meets your concrete, your panel of valves also helps to seal the dam from the back of the wall. So once you've got your wall in place, that becomes a lot easier to do, having that protection from the front.
Thank you.
Are there any questions here in the hall?
Thanks, Marius. It was very interesting indeed. What is your margin of error permitted when you are doing this profiling? That's one question. And the other is, could you not make use of photography, underwater photography, to get a more accurate profile of the obviously pretty broken up rock?
Yes, thank you, Roger. I believe, I think from an accuracy perspective, you can actually see on this photograph right now, you'll see the different levels of the top of the wall. We had an accuracy of about 15 to 100 millimeters, which was unacceptable, especially once you start scaling up and overlapping your blocks. You start getting what I refer to as the roof tiling problem. If your one tile overlaps with the next and it's a little bit out, the next one is out with that plus any further inaccuracy, and eventually this will end up going somewhere to Gansbaai. So accuracy, when you're constructing a wall with no let's say grout between the joins, that becomes very, very important, and one of the reasons why we're leaning towards automation. So yes, Roger, the first technology we reached for was either videography or sonar. Now, as you can see in this photograph, you're in the surf zone, so all this white water that you have here, where you're constructing in, got tiny little bubbles in, and those bubbles refract any light or sound and results in absolute garbage out. So we've had guys with little boats with side scanners here. We've had a variety of technologies to try and map the seabed for us accurately. I think the other challenge is the fact that the wall is half in the water and half out the water, depending on the tide. So you'll only get half the picture sometimes. if you get a very, very calm day at a spring high tide, you might be able to go and scan the entire wall section. Now, the problem with that is that, as you correctly said, some of the rock is relatively unstable or can be broken up. So if you're scanning your whole wall, going and precasting it off site somewhere, which sounds fantastic to me, but you have that delay in you casting all your blocks. You think that's what the rock profile looks like, and you come and put it in a week, 2, 3, a couple of months later, and something has changed. So for us, the most reliable way to do it was to physically probe, like 100% sure that what you get out is accurate. Then reduce the amount of time between your profiling and your installation of your block. The closer that comes together, the more accurate your result is. So hence our kind of stretch goal of being able to profile, cast, and install in one day, from a cost perspective, but also from an accuracy perspective.
Yeah, thank you. This is Pat Hart here.
Hello,
Two
Pat.
questions. First of all, what about the amount of sand that gets washed in? Surely you will have a problem filling up the dam with silt. Has this been taken into account, or is this not a problem? It seems a problem to me. The second question is, once you put your profiling block in that was shown as white, that white stuff, that white profiling block, you put your other precast blocks on top of that. Now, those are pre-made. They're not part of that 8-hour situation. Am I right, or am I misunderstanding something? Thank you.
The first question about sand, it is something that we might need to manage. Having, especially somebody like Pierre has been building in this site for about 30 years, there isn't much sand in this area. So we've been pumping from here. We run quite a big operation from Abergold perspective, and we do need to clean our sumps from sand with a siphoning system. But once you've got a nice big dam, you can use slurry pumps and pump that out quite efficiently. So it's something that we'll have to watch, I think, specifically in our storm seasons in the winter. But it's something that we can manage quite effectively with relatively simple equipment. Then yes, the precast blocks that I'm referring to are pretty standard. So if you look at this picture that we're looking at now, if all the blocks you can see here were cast with a standard mold ahead of time. So we've got a stockpile of precast standard blocks. And then the foundation, the custom foundation blocks have a very specific pattern in it that locks into these precast blocks. Now, this design you see now is very much almost how I refer to it as it's a sliced bread design. So every stack of concrete units fit on top of each other, but they're independent. So this section of blocks go on top of each other, and the next one goes next to it. But the design that we've done now, the blocks actually overlap each other, almost in a stretcher bond configuration.
Yeah.
Like the wall behind you. And once you start doing that, your foundation needs to be incredibly accurate.
Incredibly
precast black. Yeah.
Sure.
So that is one of the key drivers of why we went to this length of automated robotic profiling on the same day, with a reduction of time lapse between profiling, casting, and placing. That is the key. If we can achieve that accuracy, and I believe that we're taking tolerance down from about 50 millimeters error, where we were manual, down to talking less than 5 millimeters is where we need to be.
That's what I expected. Okay, thank you.
Thank you.
Thank you, Marius.
Thank you.
Thank you.
Marius, I have one quick question. In addition to the sand, what about sea life, fish and so on, also being washed in, and
Yeah.
whether that'll have an environmental impact?
Yeah, look, even the turbines that we're planning on using, which are 3-4 meter diameter turbines, are classified as fish and seal friendly. So in other words, they're very slow moving, large diameter turbines, which won't damage the sea life. And then the dam that you're building essentially becomes almost like a tidal pool, like the marine. So you'll have a sea life in there, but it'll become its own environment. I think the biggest environmental impact that this design has obviously is the footprint of your wall. So you now got the rock surface, which has marine life on it. And part of our environmental impact assessment states that we need to inspect that rock and move any marine life, physically remove it, any marine life that is to preserve. So we have an independent consultant that comes in and does that work for us, and then make sure that we're not damaging any endangered sea life for that matter. Thank you very much for everyone's time. Your interest.
Thank you very much.
I really appreciate it. Okay.
Marius, thank you so much. And Pierre, you can be proud of your son, man.
It is quite an honor to be able to respect your children. I really appreciate it.
Yes.
And,
The future's mutual, feelings mutual. Yeah. Bye. Bye, everyone. Thank you.
Thank you very much.